Hello and welcome back again to the linear algebra component of the calculus and linear algebra series. In the last video we introduced this idea of the contrapositive as well as introducing De Morgan's laws and proved how those were tautologies. And I actually lied to you a little bit in the last video and said that that was going to be the final video on propositional logic. In reality, this is actually going to be the final video on propositional logic, and we're going to introduce a very important concept that you might have already seen in the calculus component of the course, which is this idea of a contradiction, and we use this in order to construct certain types of proofs called proofs by contradiction. So let me look at this theorem now that allows us to construct proofs by contradiction. So suppose I'm given a propositional variable and I've got this theorem that says P is equivalent to not P implies a contradiction, and we use this contradiction operator without any other propositional variable in front. We kind of briefly talked about that in one of the earlier videos, that because the contradiction operator does the same thing to all propositional variables, it's often denoted by removing the propositional variable itself. So let's analyze how this is going to relate to proof by contradictions. Well, what it's saying is it's saying that if I've got a particular proposition, and I call that proposition P, and let's say I assume that not P is true, that is, that I assume that P is false. And if I can show as a direct result of P being false that that implies a contradiction, that implies two results that are kind of mutually contradictory, then that must mean that P must have been true all along, because if it cannot be false, then it must be true because it's a proposition. And that's effectively what this is saying here. It's saying that P is equivalent to supposing that we have not P and showing that that results in a contradiction. So how to prove this? Well, we prove it in the similar way as before. We need to construct a truth table, and we want to construct a truth table and show that the columns in this one here, the column of P, namely that we've got true and false, is the same as the column for not P implies the contradiction. So the first thing we need to fill out is not P. We know how to do that. We take true to false and false to true. The next thing we're going to put in is we're just going to put this contradiction operator, which takes everything to false. Right? And again, just to reiterate, we're not putting the propositional variable in front of the contradiction operator here because it does the same thing to all propositional variables. So we just denote it by this single upside down T. And that takes everything to false. So everything in that column is false. And then the final thing we need to look at is we also want to look at not P implies contradiction. Well, we want to show that this is going to come out the first value is true and the second value is false. In other words, it's got the exact same truth values as the column of P. So the first one says we've got not P is false implies false. Well, a falsehood can imply anything, so that maps to true. So false and false goes to true. Let's look at the other one now. Now we've got true implies false. Well, we know from our definition of the implication operator that that must map to false. So again, let's look. We've got the column of not P implies contradiction, and we've got the column P. Those have identical truth values, hence they are equivalent, and that statement above is proven. So this is effectively the theorem that allows us to construct proof by contradictions, right? So that's the important one. But we can also construct proof by contradictions, not for just single propositions or atomic propositions, but we can also construct it for implication statements. So let's see how we would do that here. So we've got P and Q are propositional variables, and we've got an implication statement, P implies Q, and we say that is equivalent to P and not Q implies contradiction. So let's kind of analyze this again before we prove it. That's saying that if we want to show P implies Q, what we can do is we can assume P is true and not Q is true. In other words, Q is false. And therefore, if we can conclude as a result of those assumptions that we get a contradiction, it must have been the case that P implies Q is true. So let's see how we would go about proving that. Again, we're going to prove that using a truth table. Now, unlike before, our atomic propositions are P and Q, so we need to go and fill out all our columns for P and Q. Our first statement is going to look at not Q. So we look at our Q column here. We take true to false, false to true, true to false, and false to true. The next thing that we're going to be looking at is our contradiction column. Well, we don't need to fill anything out in terms of how it relates to other columns. We know that all of it is going to be false, so we just fill in all our false values there by definition of the contradiction operator. The next one we're going to look at is P implies Q, so we look at the columns of P and Q. once again, we know how that works. That takes true and true to true, true and false to false, false and true to true, and false to true. The next piece we want to look at is P and not Q. So in that case, we're going to take the column of P and take the column of not Q. When is that going to be true? That's only going to be true when both P and not Q are true. So in other words, the first case, we've got true and false. That's going to map to false. We've got true and true. That's going to map to true. False and false maps to false. False and true maps to false. And then our final one that we want to look at is P and not Q implies contradiction. So we need to look at our column for the contradiction, and we need to look at operator and our column for P and not Q. So let's look at those two columns. So starting with P and not Q, we've got false implies false. Well, we know falsehood implies falsehood maps to true, so false and false goes to true. It's good. We've now got truth implies false. In other words, that maps to false. So true and false maps to false. Here we've now got false and false. Well, that's going to map to true. And then we've got false implies false, which is also going to map to true. So let's look at our column for P implies Q and our column for P and not Q implies contradiction. We see that the entries of those two columns are identical. The truth values are identical. Hence, they're equivalent. And that means that we finished our proof once again. So why is this useful? Just to kind of finish off the video, this is useful because these two particular types of theorems allow us to use this technique, this contradiction technique, to prove individual propositions by initially assuming that they're not true and arriving at contradictions. And we can also prove implication type propositions by assuming P is true and not Q is true, and then arriving at a contradiction, which will in turn prove the original implication statement. So that's our final video now, and I mean it when I say it this time, on propositional logic. And in the next video, we will be actually talking about first order logic and kind of talking about these ideas of predicates that we introduced in the first video. So once again, I remind you to look at the notes on the Moodle page, and as well also try the questions in the module handbook after watching this video. So thank you very much and see you in the next one.